Yesterday we talked a little bit about. I talked about the tangents, and where did I write it? So anyway, remember the optics, so all kind of bouncing that I mentioned. I forgot to mention one of the coolest applications of tangent, widening tangent, and that's stealth technology. Okay, so pretty much the same story. So you've got to deflect the radar signal away from the plane. Okay, so not back, not just away, but not so it would not go back, or less likely to go back to the source. And in fact, you could probably remember the way the it's kind of a F-117, I believe the number is roughly looks like this, So as you can see, it was made in order to have this technology developed, made of pretty much straight edges. Okay, so you don't have to deal with any kind of complexity, because then it is like a mirror. Okay, and at the same time, you might remember. So that was in the 1970s. It was developed, and then there was a B-2 bomber developed in the 80s, and it has a smooth outline, looking like this roughly. Okay, so that for that kind of curved surface to figure out where the signal, which way the signal will bounce off the surface, would be much more challenging. And then once again, you got to deal with all this business. And well, there another question related is naturally the Earth. So how do you know that the Earth is round and not flat? Anybody can prove that the Earth is not flat?
Well, I mean, you can walk all the way around it and wind up at the same place.
It sounds like a good plan, although you would have to take a ship a few times, because so that certainly that sounds like a plan. Oh well, if you come back, it still doesn't prove, and that's I understand that's the problem. With the people, some people, is that just because you come back, it doesn't prove that the world is round. I could here it is. I've taken a trip. Okay, I'm back where I was. Have I proven that the world is round? No, I just came back. That's all. So, any other plans? Anybody knows how it's done?
You can look at the moon.
Okay, how does that help?
I mean, the moon's round, so.
Well, it's it might look like this, right? And you can, but that's round too, just like the moon. Doesn't mean that it is round as a sphere. Now we know the difference now between the disk on one hand and a sphere. Or at least we were getting into that. We were getting into surfaces. So either it is a flat two-dimensional thing, or it is a two-dimensional object in three-dimensional space, such as the sphere. So just the way it looks round. Yes, so the edge is round. That we know. And we also know that the problem with movies, especially because it doesn't turn in front of us. That's really the problem with using the moon for that purpose, is that it is nasty. Yeah.
I was thinking if it was flat, then if you change your elevation, wouldn't that do? I mean, increasing your elevation significantly wouldn't increase your line of sight, right? You still have the same line of sight,
right?
Not,
right. Yeah. So yeah, if you climb, it doesn't have to be. Yeah.
You could take like a really tall structure.
Yeah.
Look at it and then walk backwards from it, and you can see it disappear over the horizon.
Okay, so that almost the same thing. But what you do is to be fair, well, you only discover that the curve at that particular spot is curved. So there's a curvature of the Earth at that spot where you conduct that experiment. That's good. That certainly is a start, but that doesn't really prove. That is actually a problem from the last chapter. Is we know that the circle has a curvature. Constant curvature. Suppose curvature is 1. Suppose the circle is radius 1, then curvature is 1. Now suppose you're measuring the curvature equal to 1. Does it prove that that curve is a circle? And the answer is yes, but it's not easy to prove to begin with. Secondly, to actually know that the whole curve has a curvature 1, you have to actually make the full trip, and then what's the point? Okay, so just knowing that it is several spots, or maybe a lot of spots of the Earth, there's a curvature. It is curved. It doesn't really prove that it comes back. It doesn't have to be. The question is really not two-dimensional. You can just think about the circle in the same manner, and you ask yourself, does it? So curved here, does it come back and onto itself, meet on the other side? And that is not obvious. That is the case. Let me give you one curve that is the curve that is curved everywhere, and yet it is not. Well, I mean, you take a parabola, you take a hyperbola. All of them are curved, and yet they go into infinity. Okay. So and then we only know a small piece of the possibly of the Earth, or maybe it continues on and it flattens out, and so it looks like this, and then it flattens out. It's also possible. So anyways, it's not easy without actually a round trip. I think it's pretty hard to actually to provide a good proof in a kind of a one-person task, because you got to build a. It's hard for a single person to do it. So because you have to build a ship, either a ship to take a round trip, or a spaceship, or something like that, a telescope. So that's a lot of work, and that's why it took a few centuries. So okay, so I hope we will revisit this issue later on. But at this point, so we're talking about surfaces as functions, and surfaces as graphs of functions. Okay, so as you can see, the function is thought of as input point. It's typically two-dimensional, and the output is a number. Okay, so all the graphs that we have seen look like this. Okay, so the input is spread out along the plane, maybe everything. The issue of domain still comes up, because you still can end up with dividing by zero, roots, and so on. So there might be holes in the domain, there may be gaps in the domain. So those issues also come up. They're just not as prominent as in Calculus 1, for a simple reason. It is just not. It is just. But by now there are bigger issues. So the metaphor is the terrain. So map of a region with the elevation of the value of the function. So each location gives you elevation. Okay. So we are now interested in studying those elevations one point at a time, and that's the issue of the flat Earth. Is that why why it comes up in the first place? Because if we look at as we did yesterday, if we do not go far away from a given point on the surface of any surface, on any point of the surface, it looks flat. Okay, so unless it is very rugged, you're gonna feel like you're standing on a plane, which might be inclined, which is what we're concerned with right now. So it might be inclined plane. Okay, so it might be curved, but if you are not going too far away, it looks like a flat plane. Literally, a plane might be like this. It doesn't have to be flat. It could be like this, but it is flat, and so that's how we're gonna proceed. We're gonna approximate the curved surface with a plane at every single location. So just like with curves, at every single location there is a tangent line, and that is so you get a bunch of tangent lines for every single point. That is quite a picture, actually, if you think about it. So this is what it looks like, all right? Tangent line for every single point. And now we are in an even more complicated place, because now the surface, and at every single place of the surface location on the surface, there's a plane that approximates it. Okay, so we are looking for that plane. Long-term goal is to find a way how to discover that plane. So we are now living in for a moment, because we still simply have to figure out what planes are, how to represent them mathematically, but also what the planes are. We reviewed the tangent line issue. Okay, so and the issue of the formula of the of the line is a point plus, over here, point plus t times the direction vector, okay? So we want a similar equation for the three-dimensional space, plane in the three-dimensional space, okay? So to begin with. And, okay, so this is discussion. So lines, planes look like this. So linear functions of x and y represent planes. So unlike with straight lines, it is hard to refer to Euclidean geometry as something that helps us to understand things, because plane geometry is typical, studied in high school, in the stereo geometry not as much. So we actually have to figure out what plane is to begin with in order to use it. Okay, so we don't try to be too fancy about it. We just say, well, when it is given by an equation like that, that's a plane. So we just say that this is a plane. A plane, but this is a particular kind of plane to begin with, is a plane that is also a function of x and y. So, because there could be a vertical plane. Remember the same issue in dimension 1, calculus 1, you represent curves as graphs of functions, but then there's a vertical plane which is out of reach at first. And that's why we need parametric curves. Okay, so that's why we're starting with this. We have looked at the plane. Well, suppose we don't know what it looks like. It's just a sloped, possibly sloped a plane. And now what we do is that is a typical way of dealing with functions of several variables. Not the typical, but really the main way of dealing with it is to fix one variable at a time. Okay, so hypothetically, if you have some kind of process and you have parameter, one parameter is say pressure and the other one is temperature. Say something dependent. You fix pressure and see how that quantity depends on the temperature, and then you fix temperature and see how the change in pressure changes that quantity of yours, whatever you're looking at. So that's exactly what we did here. Okay, so the simplest way to do it is say fix y equals 0. That's the equation, which is nothing but a straight line. This is a familiar straight line. And it is in a particular location. If you look at it, this is the independent variable. This is the dependent variable. So it's on the xz plane. Okay, so that is what I plotted here. On the xz plane, we have some kind of straight line. Okay, and then we do the same for the other variable. Okay, and so we fix x equals 0. And then once again, it looks like a z dependent variable depends on x and y independent variable. Okay, and so that's again a straight line. But this time it is on the yz plane. Okay, so maybe like this. So once you have these two, that is almost all you need, because two lines intersecting lines. We'll take a point here. That point is, by the way, as we have established, this is like the z-intercept. So this is A over here. Okay, the point. And then we fix z value, fix x value, y value, getting two straight lines, and that is already pretty much all we need to find our plane. Maybe like this. So it doesn't give me the whole plane. It's harder and harder to visualize it. But I imagine that there are two lines like this, starting at the same point, and then they define a plane. Okay, so. So that's pretty much how we do it. So then A and B, rather B and C here, have a specific meaning as slopes. They are slopes, except instead of having one slope, we have two. And well, this one is still fair to call it a slope, because the slope in the plane, in the xz plane, there is one slope, and then in the yz plane, there is the other slope. Okay, so, and then they reappear here as the coefficient of x and y respectively, while the value of A is that y-intercept is a point. It's not a slope. So if once again we want to put it this way, so z is equal to a plus bx plus cy, we can identify this as the z-intercept. Intercept. B is the slope with respect, well, let's say it's x slope, and this is y slope. Okay, because the straight line, because this surface is a plane, so there is no variability of the slope. So same throughout. Throughout the graph, the slope will be the same. For example, I don't have to fix y equal to 0. It won't change if I pick, say, y equal 1. What's going to happen? Not much. It will be z equal a plus bx plus c. What's the slope? The same thing. So it was b, it's still b. Okay, so if I fix x equal 1, then my equation becomes z equal a plus b plus cy. So once again, what's the slope? The slope is of this line is still c, except that this part will change. Okay, so instead of having our plane cutting out a straight line on the coordinate planes, these are x, z, and y, z planes, we are talking about planes in general. So these are planes. What are these? What kind of planes are these?
I guess y1 would be parallel to the x, z axis.
That's right. So it's saying that y equal 0 gives me the this, right? This is x, y, z, x, z axis. But if I say y equal 1, the result is this. This is the 1 on the y axis, and I have pretty much almost identical plane, except it's been shifted. So this is y equal 1. Similarly, if I start with the x equal 1, then x equals 0 tells me where things are. So this plane is x equals 0, just like this was y equals 0. And now I'm moving towards x equal 1 over here. And so what happens is it's just a shift of that plane. And this is my new plane. This is x equal 1 plane. Okay, so y equal 1 plane, shifted y equals 0 plane. And then, as you can see, what happens then, once we pick that plane, we're looking at the intersection of our plane, that plane, with one of these planes. And then generically, what happens when two planes intersect, they create a line. Okay, so as you can see, that's the green line, the purple line, as well as the black line at the bottom, also important, the intersections of two planes. So that's one way of thinking about lines, is that the intersections of two planes. Okay, even though the parametric representation is certainly better because it's so simple. Anyway, so then, as I said, the same slopes throughout the plane, which is not going to be the case for general functions of two variables. So, but we have to start somewhere, and that is the starting point. Is a straight plane. Okay. So now this is not really hard to remember. The equation. This is the equation of a plane. So three coordinates, three coefficients. We're getting one extra coefficient in comparison to the line. Okay, that actually is something to contemplate, is what that progress that we make from, say, y equal a plus bx. Okay, so that is calculus 1 situation, and we introduce one extra variable, and then we have, instead of having two variables, we have three, but still one is independent, and then this time it's two dependent variables. And then what happens is the graph of the original function was a curve in the plane, and this is a plane in the three-dimensional space. Okay, so then you can imagine, or try to, I would like to try to imagine that if I have three independent variable, one dependent variable, such as, say, u is equal to a plus bx plus cy plus dz. Okay, so it's a function of three variables, still linear function, really easy to compute, but now, can you imagine what its graph looks like? Well, first of all, where is it located?
R4.
In the four-dimensional space, that's right. So which is hard to imagine, obviously, but the graph itself is simpler than the bigger space, and the graph will be only three-dimensional. Okay, so one-dimensional in two-dimensional space, two-dimensional in three-dimensional space. This will be three-dimensional in four-dimensional space, and so on. So that is the unfortunate fact of extra complexity in comparison to parametric curves, where progressing in dimensions did not really change a lot of things that the way we did them, and the visualization was fairly simple because the curve is a curve in any dimension. Okay, and a vector is a vector in any dimension. And but here, as you can see, what we are studying already, we go in dimension one, the thing itself becomes thicker. Okay, so from a line becomes a surface, and then in the next step it becomes three-dimensional space, and that's why the visualization is much harder. Okay, so what I want to do now is also find that there's a better equation. There's a better way to represent the So what I mean is the point slope formula. Okay, so for the line first, so it is, remember y minus, how should I put it? Y minus b equal m x minus a. Okay, the point is, on the plane is AB, and the slope is m. Okay, familiar? Okay, so for the line, and now we going up in dimension. We know that the equation will look similar if we are speaking for the line on the plane. Okay, now we are moving on to where we are now. The point, I suppose there's no good way to put it, slopes formula, because there are two slopes for the plane in Earth in space. Okay, so then you can think about what's going to happen is, instead of having one point with two coordinates, there will be three. So it's a point that will be ABC, stating for the coordinates of that point in the xy plane, and there are two slopes, say m and n. Okay, so roughly we know the way it's gonna look like. Look at it. It doesn't have the same form, but the slopes are up here, as you can see, simply as coefficients of x and y. So m and n will be coefficients of x and y, and then instead of having, as we did, the z-intercept staying as a separate number, we will have something more similar to this. So let me just write it out. It will be z minus c equal m x minus a plus n y minus b. There might be a different name for this formula, but I like it the name because it clearly shows the progress from calculus 1 to calculus 3, from dimension 2 to dimension 4. And you can also start thinking about what's gonna happen in higher dimensions. So let me try to illustrate this with a little picture. So, so this is A on the x-axis, B on the y-axis, then Z on the C on the z-axis. Okay, so this is z-axis. Okay, and so that point is here somewhere. That's my point ABC. Through that point, that's the only point that we know for sure is on the plane. And now, which way does the plane goes? It goes in the way of, according to what the previous discussion is, the slope of M will be along the x-axis, in the direction of the x-axis. That's the slope. That's how far we either climbing or going down. The slope is M. We're moving. If we're moving in this direction, okay. Let me make that picture. Okay, so if we're moving in this direction, slope is M. Okay. So think about it. When I'm moving along this line, what's happening to Y? What's happening to Y?
It's constant.
It's constant, so which means that this term disappears, right? So y is equal to b, so that there is no term like that, and we're left with literally an equation of a straight line, on within that plane, within which plane that plane. Okay. So as I said, let me just write it. Let me write it. So it will be z minus c equal mx minus a. So that the equation that I wrote is this. Okay? So we are staying within this plane, which we just discussed, that one of those planes, the horizontal plane that parallel to the xz axis, xz plane. Okay, so we're staying within that plane, the blue one over here. And then we realize that there is no change of y because y is fixed. And then we are purely, we end up with a two-dimensional situation, a straight line. The meaning of the slope is absolutely clear. That's the whole equation. Okay? Now, we're doing the same thing. I think I'll try to copy this. Where is it? Oh, here it is. Okay, let me try to copy this. Okay, so now we're doing the same thing, but we're now moving in the y direction. So we'll raise all of this. So we are starting. The starting point is still the same. We're still moving in the. We're still in the point ABC. Okay, so this is where we are, but this time we're moving in this direction. Okay. So then we're staying in the plane that faces us. This plane, okay? And which means that x is fixed. X is fixed. Okay, so this is A, as a matter of fact. X is fixed, and but y changes. This is B, and which means that we end up with this term disappears, right? From the equation, we're left with z minus c equal n y minus b, and the slope in this direction is n. Okay, so the graph will look like this. Well, it could go up or down. Let's suppose it goes down, just to keep it simple. Okay, so you certainly, since this is a straight line, I could certainly continue on here. I could continue on there, and if I put these two together, it will give me the plane. Two straight lines to the same point in three-dimensional space will determine a plane. Okay, so let me try to do that. So I don't want to explain the meaning of the slope. I hope is clear that I'm using the word slope in the exact same meaning as it was elsewhere. It's just a straight line. It has a slope going up, rise over the run. There is nothing tricky about that. Okay, so let me try again to do this Okay, I just want to see if I can bring these two together and overlap them. Okay, so let me erase the things that are not kosher anymore. Well, not this. Okay, so that is the one, and now I'm taking the other. Okay, whoops. Okay, let me start over. Okay, carefully. Okay, so it's the same curve, so they should overlap perfectly. I hope so. Oh, it's close enough. Okay, so that's you can see it, right? So if I erase all that business. Okay, so you can see the progress along the x-axis gives me one line, progressing along the y-axis gives me the other one, this one. Okay, and then together they hopefully determine, look at these two straight lines, they determine a plane, which I'll try now to suggest what it looks like. Okay, so that is our plane. Okay, it comes from, once again, from these three numbers, or 5 numbers. So the point given by 3 numbers and two slopes. Okay, so now the fun part is that this equation is actually can be significantly simplified. So let me write it out again. So the equation is z minus c equal mx minus a plus ny minus b. So we could try to recognize this. Can you recognize this as something familiar? So x slope here, and at the same time we have stepped away from x from a into the x direction. So if we are, well, let's concentrate on the xy plane, and let's ignore z for the time being. Well, just looking at the right hand side, we are at the point AB. Okay, and then we're making step away from a like this towards x. So then this is x minus a. Okay, and then there is a second number m. Okay, so and then there is a number like this. Okay, so this is y, and this is y minus b. Okay, so in other words, what has happened is we have moved away from the point AB like this. Okay. Okay, so we are right now concentrating on the input variable of our function. Okay, and because remember now the inputs are complicated and the output is easy, just a number. Okay, so unlike with parametric curves, it's totally flipped. So we stepped away, and this vector here is x minus a, y minus b. Okay. So we step away from the point we're studying, point AB, and the vector has coordinate x minus a, y minus b, and then that vector somehow appears in this expression. So once again, do you recognize the familiar construction recently?
I mean, it looks like a circle with the equation of a circle or an ellipse, if I'm in an
No, you don't have squares. It does, but you don't have squares. And so you multiply x by a, you multiply x by a by itself, then you have, then that's how you get the square. And here instead I'm multiplying by a number which, okay, so let me give you a hint. Compare, well, m and n can also be formed into a vector. Okay, now can you see the expression that I'm looking at? So this expression in terms of these two vectors.
Oh, it's the dot product?
It's the dot product, that's right. It is the dot product. So indeed, when I do dot product with these two, I will multiply x's by x's, y's by y's, and add them together. So indeed, the dot product of these will be x minus a m plus y minus b n. Okay, so so why do we care? We care for one. Imagine that I hypothetically move to the next dimension. I will have, say, I don't know, the third dimension is u minus, say, k, whatever. So you can, if you have a function of 3 variables, as I suggested there, the plan still works out. It will be still the dot product. Every time you'll have a dot product, except there will be more components of those vectors. Okay, so this is the simplest case is when you have only 2 vectors, 2 dimensions, and those 2 vectors multiplied give you only 2 terms. But in n-dimensional space, that expression over there at the top will have n terms. Okay, but the dot product, that's the advantage of the dot product, it now becomes entirely, it is very compact, and we can rely on everything we know about vectors and dot products. Okay, so let me try to write it out. So we want to take advantage of this. We want to take advantage of this, and so let me z minus c. So it's nothing interesting is happening on the left because it is a function. It is a numerical function. So the output is just a number. Okay. So on the left, let me just write the way we did. So it's x minus a, y minus b, dot product, m n. Okay. So once again, this is like the increment. The increment of the input, component-wise, and these are the slopes. So the 2 slopes we put together in a vector, and that vector becomes very important. If you have 3 dimensions, you have a vector, 3-dimensional vector. Okay, so the only thing that we could try to improve is the first one. Okay, so suppose, let me go this way. So I want to make it as much coordinate free as possible. Okay, so what I'm going to do is I'm going to introduce the variable, say p, which is xy, and then we have the second, that is our variable point. The point is fixed at p naught equal ab, ab, and then let's call it m. So this is fixed point. Okay, this is the variable. And thirdly is that a vector that contains all the slopes. So slopes, m, let's say in capital, m, n. Okay, and then what happens is I can write it now in the point slope in the form that is vector. Okay, so it will be 2 vectors. The last vector is simply m, but the first vector is actually quite simple. It's simply p minus p naught. Okay, that becomes my new equation for the straight line. Okay, so this is the straight line through point P naught with slopes m. So slopes are put in the vector again. So any vector naturally, both P naught is arbitrarily chosen on the plane, and at the same time, the slopes are, we can go in any direction. It's not exactly right, though, the way I put it. It's not really through the point P naught. This point P naught is in the space of inputs. There is the, if you want to speak about the graph of this, then the actual point is A, B, C, the three-dimensional space we are living in. So that's why this one can be further improved if we are abandoned for at least for a moment the idea of thinking of planes as necessarily planes that are represented by as graphs of functions. So what if we think about it as just any plane? So it would include vertical planes as well. Okay. So let me try to write it out in a better way. Okay. So in Rn, so given a point P naught, a vector M. Okay, that's it. So there's a point and there's a vector in the n-dimensional space. Then this is what I write. P minus P naught dot M is equal to 0 is a straight line. I'm sorry. Well, we don't have to say straight, it's plane. Wait a minute, did I say line here? Plane. Plane. A straight plane. In a moment, you will see why this is a plane, that's not a line. So a plane for a given point, and what is the meaning of the M? That is the question. So a point, and it contains P naught. First of all, why does it contain P naught? Well, if I choose, remember P is the variable. If I choose P is equal to P naught, then of course P minus P naught is equal to 0. So yes, the equation is satisfied. If P is equal to P naught, we have our equation satisfied, which proves that indeed P naught lies on our plane. Now, what is the meaning of M? What is the meaning of M? Let's try to think about it. So we're stepping away from P naught in the direction of P, in the direction of P. Okay. Okay. Then this vector is P minus P naught. Okay. So where is M? Now look at the equation again. P minus P naught, dot product M is equal to 0. What does it tell you about M?
It's not in the same plane.
It's not, but we have specific information about when two vectors dot product equals 0. Dot product of vectors is equal to 0. No? What's so special about 0 dot product?
The vectors are orthogonal.
Orthogonal, that's right. That's right. So this means orthogonal. So in other words, this is where vector M is pointing. Okay? Now, just one vector or there is more? Well, there is M is fixed, so I did it in kind of the wrong order, but the M is fixed. M is fixed. And P naught is fixed, so this is fixed. And then what we're supposed to do is, let's find, what's the meaning of an equation? It means that find all P's that satisfy this equation. Okay, that's how you find the geometric, the meaning of the geometric meaning behind the formula. You find all P's satisfying this equation. So let's try it. Turns out that what we have discovered is that P minus P naught is perpendicular. P minus P naught is perpendicular to M. Okay, so that's the key condition. That tells us what P's are and are not allowed. Okay, so any point that I find here, I will check the angle, and if the angle is 90 degrees, then we're okay. Okay? So, imagine this is a three-dimensional space. Well, I could put it this way, that's still okay. And this way, that way. So you see how the plane is forming? So as long as the angle is 90 degrees, all of these p's are allowed. Okay? So imagine that this is M. This is M. Fixed. The point is also fixed. So this is all arrangement is fixed. And now I'm trying to find vectors starting from here that are perpendicular to this one. So one, another one, another one, another one, right? So all of these are good, and they're pointing in all directions, but they cannot point like this. Okay, they all remain 90 degrees, and if you put something like that on a plane like this, you know that all the vectors in the plane will be perpendicular. If a vector is sticking out under any angle below or above the plane, it's not in the plane. Okay, so that is roughly the idea that we're gonna pursue. And once again, this is the problem. So we express the dot product. We express the equation of a plane in the n-dimensional space as the dot product of increment times a fixed vector, which we'll understand as if it is made of slopes. Okay, so we'll resume to next week.